Hey everyone, and welcome to The Explainer. Today, I'm stepping in as your high-speed exam coach because we are going to blitz right through questions 1 to 50 of the M7 Aviation Maintenance Question Bank. Now, if you're studying for your certification, you already know this material is incredibly dense, but my goal today is to take all that technical data, pull out the absolute core principles, and lock them right into your memory. All right, are you ready? Let's dive in. But wait, before we get completely lost in the weeds with tools and hardware, we need to set the stakes. Question 49 of the bank asks a seemingly simple question. Why is weight and balance so important in aviation? Well, the answer isn't about fuel efficiency, and it's definitely not about packing in more luggage. The singular, correct answer is to ensure safe flight handling. This whole explainer, and honestly every single question we're covering today, isn't just about passing a test. It's about learning the exact, uncompromising standards required to keep an aircraft safely in the sky. And speaking of safe flight handling, nothing represents that better than the sheer, undeniable math of aviation. Question 3 gives us the exact formula for calculating the center of gravity for an empty airplane. Center of gravity equals distance minus force times length divided by weight. Just seeing this equation really proves the immense technical depth required of us. You aren't just turning wrenches out there, you are calculating the literal balancing point of tons of metal. So, to get through these first 50 questions as efficiently as possible, here's our game plan. We're condensing the bank into 5 core modules: tools and diagnostics, hardware and fasteners, physics, elements and safety, manuals and ESR regulations, and finally, ground handling and procedures. Let's kick things off with Module 1, Tools and Diagnostics, because precision is literally everything. All right, you've got to lock down these rapid-fire associations so you immediately know what tool fits the job. If question 8 asks about testing a coaxial cable, boom, your brain should jump straight to time domain meter. Question 14 on rigid borescopes, just remember they come with several viewing ends: forward, lateral, oblique, and reverse. If you're examining jack screws for wear in question 15, you reach for a micrometer or a vernier caliper. And what exactly does a vernier caliper do? It measures both inside and outside dimensions. Finally, if you're dealing with sandwich composite panels and need to find hidden damage, ultrasonic inspection is your go-to. Now, the crucial point isn't just knowing the tools, but knowing exactly how to use them safely. Question 16 highlights a trap you do not want to fall into: confusing your electrical checks. If you're using an ohmmeter, that circuit component absolutely must be isolated, and the power source has to be completely removed. But if you're using a voltmeter, it's a totally different story. It must be connected directly across a component to actually make a measurement. Make sure you know the difference. Moving right along to question 17, let's look at visual inspections. We've got a magic number here, 500. When you're using color contrast penetrance to hunt for tiny, microscopic flaws, you can't just shine a standard flashlight on it. You must illuminate that inspection area to a level of at least 500 lux. Without that exact level of brightness, you seriously risk missing a catastrophic flaw. Okay, on to Module 2, Hardware and Fasteners, holding it together. Let's lock these rules in for the next block of questions. Question 21, mushroom head rivets. Why do we use them? Specifically for skin coverings to provide maximum strength. What about question 22? If you find broken strands in a boating cable, you do not try to patch it up, you replace the complete assembly. When you're installing a flexible hose, question 25 says you always leave 5 to 8% slack of its total length. That's to account for changes when the pressure hits. In solid riveting, remember it's the pre-formed head that receives the blows via a snap. And finally, why do we lubricate bearings? Primarily to prevent undesired friction, not just to stop corrosion. You've also really got to pay attention to the precise terminology for fitting parts together. An interference fit might sound like somebody messed up, but it's totally intentional. It means the shaft is deliberately bigger than the hole, so you need force or temperature changes to mate them. This is completely different from rivet clearance, which is just the mathematical difference between the size of the hole and the rivet's diameter. Here's another super strict numerical rule for question 29, 2%. If you are checking an aircraft chain and you measure an elongation in excess of just 2% on literally any section, you can't just swap out that one bad link. The entire run of the chain must be completely replaced. Margins in aviation are razor thin, guys, and 2% is the absolute hard limit. Next up, Module 3, Physics, Elements, and Safety. Basically, battling the environment. Look, Mother Nature is totally unforgiving out there, and the bank tests you on these exact threats. For question 32, You need to know that glaze ice isn't just an annoyance, it's the most severe and dangerous form of ice formation on an aircraft. For question 34, it comes down to material science. When lightning strikes composites, it leaves physical burn marks because those materials just cannot conduct extreme electrical currents like aluminum can. We also see the effects of extreme heat. Overheated springs will completely lose their mechanical compliance. And lastly, keep an eye out for multiple element damage, or MED. That's widespread fatigue where cracks start showing up in similar, adjacent structural elements all at the same time. Fighting back against that environment, especially corrosion, requires a rigid step-by-step process, which is exactly what question 36 asks. Look at step 1. Before you even think about touching the rust, cleaning and stripping the protective coating is mandatory. Only after that do you move to step 2, the actual removal of the corrosion. Then step 3 is neutralization of the residue. Step 4, check for damage. And finally, step 5 is restoring that protection and paint. You absolutely cannot skip or reorder these steps. All right, on to Module 4, Manuals and EASA Regulations, the Law of the Hangar. You could be the absolute best mechanic on the floor, but if your paperwork is wrong, that plane isn't flying. Questions 38 through 42 really hammer these definitions. Installing new components? They must be checked against an EASA Form 1. When you see ATA 100 specifications mentioned, it's talking about the Illustrated Part Catalog, or IPC. The MEL is your minimum equipment list. It spells out exactly what equipment must be serviceable to make the aircraft legally airworthy. Inside the IPC, you'll use an effectivity code to find specific aircraft subtype data. And finally, a counterfeit part is defined simply as an illegally produced part. Question 24 really nails the core philosophy behind all this red tape. The procedures and techniques for a visual inspection must be such that they produce the same results from different inspectors. This is the whole ballgame. Safety relies on total consistency. Whether it's inspected on a Monday in London or by someone else entirely on a Friday in Tokyo, the procedure has to guarantee the exact same result. And finally, Module 5, Ground Handling and Procedures, Boots on the Tarmac. These ground rules are completely absolute. Let's blitz through this final stretch. Question 44. Before you lower an aircraft from jacks, you must ensure the brakes are off. Who handles the walk-around inspection? It can be accomplished by either the flight crew or the maintenance crew. When should you de-ice an aircraft? As close as humanly possible to takeoff time. If you replace an onboard computer, you must follow it up with a functional test. And a zonal inspection? Question 48 tells us that's a general visual inspection of an area to detect obvious unsatisfactory conditions. Now, this strict sequencing is literally life-saving when you're dealing with massive electrical power on the ground. For large aircraft, you never just walk up and pull the external power plug out. Step 1, switch off the external power at the source. Step 2, then remove the plug. And step 3, if you're going to remove any electronic equipment, you must trip and tag the applicable circuit breakers. It's all about sequential safety to protect the aircraft and, way more importantly, to protect you and your team. So, stepping back and looking at the whole scope of what we've covered today, from question 1 all the way to 50, it becomes crystal clear. These aren't just arbitrary hoops we jump through to pass a multiple-choice test. Whether we're talking tools, hardware, weather threats, or paperwork, this is the global language of aviation safety. Which leaves us with a final thought to ponder as you get back to studying. Why do we obsess over these strict rules? From a relentless 2% limit on chain elongation to knowing exactly how a voltmeter functions to the precise math for the center of gravity. This obsession with standardized precision is quite literally the only way we conquer gravity and guarantee that everyone, on every single flight, gets home safely. Keep that in mind the next time you open your manuals. Thanks so much for joining me on this explainer, and I'll see you in the next one.